Thank you all for being here. In this talk, we'll discuss the isolation mechanisms that support secure multi-tenancy in data centers and why we need to rethink their design. So let's begin our discussion with SGX. Now, SGX at a high level were a set of ISA level instructions that were added to the x86 chips alongside the supporting microarchitecture to enforce stronger isolation at the hardware level. However, pretty soon academia came forward suggesting that SGX is susceptible to side channel attacks. Now, Intel acknowledged it as a fact, but continued to downplay it, suggesting that these attacks are pretty niche and perhaps not that feasible to be carried out at scale. But with the discovery of Spectre and Meltdown, clearly these assumptions were disproven. And soon after their discovery, Foreshadow was discovered, which basically broke some of the most basic confidentiality guarantees of SGX. Now, to add insult to injury, the performance overhead of fixing these vulnerabilities was also fairly non-trivial. So for Foreshadow, Intel had to disable hyperthreading, which in its worst case scenario can incur an overhead of as high as 50%. So clearly we can see that SGX or other TEs have deficiencies, which can be broadly categorized as A, weak isolation because the tenants share microarchitectural state. B, SGX has no mechanism to enable post-load integrity checks on the computation that is running inside an enclave, such that the code that is running these checks can reside in an independent, isolated address space. And C, the entire ecosystem is so opaque that Intel's microcode is encrypted, and anytime there's a vulnerability, Intel has often taken several attempts to fix it because patches have often been incorrect or incomplete. So clearly we can see that the current state of the art of trusted hardware cannot really be trusted. With these deficiencies in mind, we present our research, that is isolated monitor execution, where our first goal is to enforce dynamic security invariants on the application to provide post-load integrity guarantees. And how do we achieve this? So in IME, the application developer writes the source code, which has the core application logic and the corresponding security checks. The compiler then generates an application binary and the corresponding security monitor. Now, these two entities are then uploaded on the untrusted data center. The application runs in what we call a top half pipeline, and the monitor runs in the bottom half pipeline. Now, it is important to note that these two pipelines are physically isolated from each other and share no microarchitectural state. Now, in order to enable the monitor to introspect or enforce its software-defined checks on the monitored thread running in the top half pipeline, some part of the top half pipeline is mirrored in the bottom half pipeline. And we'll get into the details of that later in the talk. The second goal of our research is to provide strong microarchitectural guarantees for all the app processes running in the top half pipeline, be it monitored or unmonitored. And then last but not the least, we also want to have a software readable description of our microarchitecture. And in order to do that, we're implementing this in Chisel, which is a Scala-based DSL for hardware construction. Now, the overall outline of the talk will basically be a lightning tour of SGX so that we can understand the fundamental design flaws that cannot be fixed with some incremental engineering. It'll then be followed by a detailed discussion of the IME design. And then we'll close the talk with a discussion on related work and open challenges. So let's do an overview of SGX. Now, this is a standard address layout of an untrusted host process running on an x86 machine. So SGX embeds an enclave within the user address space such that the enclave has its own stack, heap, data encode segments. What's even more interesting is that it isolates the enclave such that the untrusted host process itself cannot access the enclave pages unless it invokes the EENTER instruction. Second, it's noteworthy that the enclave runs in ring 3, which is the least privileged level, but it has access to the entire address space of the host process. But it cannot issue syscalls. So for that, it has to rely on the host. So for example, for write IO, all the data must be placed in memory accessible to the untrusted host. Similarly, for read IO, all the data must be pulled from memory, which is again accessible to the untrusted host. And then in order to switch out of an enclave, the hardware invokes the EEXIT instruction. Now, in order to support this isolation, the SGX hardware maintains what is called an EPCM, which is an enclave page cache map. Now, it's a data structure which basically has metadata entries for all the EPC, that is the enclave page cache. this data structure can only be modified by the SGX instructions. The overall purpose is to sort of consult this data structure anytime an EPC page is being accessed in order to guarantee that no unauthorized accesses are made, such that no non-enclave code can access enclave pages. Another level of confidentiality is sort of added by what is called a memory encryption engine, which encrypts all the outgoing memory writes to the EPC and then decrypts the data of, for incoming reads and also performs integrity checks on that. So this essentially summarizes how SGX works. Now let's look at the design flaws in SGX. So it is vulnerable to hyperthreading side channels. Now what does that really mean? So let's look at this diagram here that sort of represents two logical computation or two logical cores running on one physical core, where one set of logical computation is encoded in blue and the other one is encoded in yellow. And let the blue encoded computation be the enclave code and the yellow one be non-enclave code. So we can clearly see that while the front end of this pipeline is isolated, post the instruction queue stage, all the microarchitectural state is actually shared. And it is this very contention that leads to side channels. Now, SGX is also vulnerable to cache-based side channels. So how does that work? So in Meltdown, we saw that there is a race condition between a memory access bringing a value into the cache and then that value being computed upon, and the performance checks that the hardware performs on that memory access. Now, if you look at SGX, an untrusted host embeds an enclave within its address space. So the untrusted host and the enclave share the L1 cache. So the untrusted host can load an enclave and wait for it to bring a clear text secret into the L1 cache, and then leverage again a meltdown style attack to leak those secrets. And this is exactly what we saw in the foreshadow attack, where this thing called the L1 terminal fault was the underlying cause for all the secrets that were brought to the L1 cache being leaked to non-enclave code. And I would recommend that you read the foreshadow paper for more details. So now let's talk about the IME design and how it actually works behind the scenes. Now, our high-level idea is that there's a dyad, which is essentially a monitored application thread, and the corresponding security monitor, which is the dynamic integrity checker. Now, the second element is that this monitor will run in the bottom half pipeline, entirely isolated from the top half pipeline. So there'll be no sharing of the microarchitectural state. And then third, in order to facilitate this introspection of the top half, the bottom half can actually read the top half instruction sequence and the register state. So the top half ISA level register state will be mirrored in the bottom half CPU. And then the bottom half pipeline can also stall, resume, or raise exceptions in the top half pipeline. Now, let's look at the sample, sort of a simple address space layout of a dyad running an IME hardware. So for the top half pipeline, the monitored thread, again, similar to SGX, is embedded within the user address space, such that it has its own stack heap data encode segments. And then these addresses are essentially mapped to top half RAM pages that have been reserved by this monitored thread, such that no other top half thread can access these pages. So logically, it's somewhat similar to EPC pages. Now, for the monitor running in the bottom half pipeline, it is the only entity running in the entire address space. So there's no system software running in the bottom half pipeline. And then the monitor is basically maps to the bottom half RAM pages that have been allocated to it. Now, a sample security policy which works very well for IME is CFI. So CFI essentially dictates that your program execution should adhere to a static CFG, a static control flow graph. And what does that work like? So if you look at a CFG here, there are two possible call graphs. So one is that follows the left side of the branch, the left branch, to reach the bottom node. And then the call graph 2 follows a right branch to reach the bottom node. Now we can clearly see that if we enforce the static CFG on our left on these two call graphs, call graph 1 is a valid execution, whereas call graph 2 is not a valid execution. Another important thing to note is that CFI can be easily performed using just the addresses which are reflected in the register state. So it is an important prerequisite of all the security policies that can be expressed using the IME design, that they only can introspect the register state, the top half register state, and nothing else. So it's important to sort of keep this idea in mind. Now, let's look at the IME microarchitecture in more detail. So we have our top half pipeline, which follows an out of order execution. And then the bottom half pipeline is somewhat simplistic. It's sort of this 5-stage in order execution model. Another key element is what we call a code pointer table. Now, this code pointer table is essentially a key value pair, is a list of key value pairs, where the key is a top half PC value that triggers the corresponding monitor code in the bottom half pipeline. So anytime the top half PC value matches an entry in the code pointer table, the bottom half pipeline will trigger the corresponding monitor code. The second element is that the bottom half hardware copies the top half instruction stream into the circular buffer. And then the bottom half ISA is also capable to operate on the bottom half state and the top half stream state. Now, what does that look like? So we have here like a sample compare instruction, which says that for a particular top half PC value, compare the top half input register with the bottom half B1 register. So the idea is that for a particular top half PC value, the value of TI0 has been snapshotted, and then that particular snapshotted value will be compared with the bottom half register B1. Now, the third element is that after these checks have been performed, the bottom half pipeline can basically stall or zap the top half instruction retirement and memory writes. So if these checks execute in the bottom half pipeline successfully, then the corresponding top half instructions in the top half pipeline will retire, or they will be squashed. So now let's look at a more concrete example of a monitored thread and a bottom half monitor code. So in the top half, we have a bunch of move instructions followed by a call instruction invariant. Now this call instruction takes register RCX as an operand, and this RCX is being updated in the second move instruction in our top half code. The monitor code essentially has a move instruction that updates the top half PC value. And then for that PC value, it basically looks up or uses the snapshotted value of the RCX register and compares it with the value in the code pointer table, which sits at the base address in the bottom RDX register. Now, if the RCX value matches the value expected in the code pointer table, this check will be successful, or else the check will fail. Now, let's see how these sequence of instructions are executed across these two pipelines in parallel. So at stage 0, this is the situation where the call instruction is sitting in the fetch stage, and all the initial move instructions are in different stages of the pipeline. And the first move instruction in the monitor code again is sitting in the fetch stage. So in the next cycle, all of these instructions move forward because there are no dependencies. In the next cycle, all the move instructions move forward, but the call and compare instruction in top half and bottom half respectively stay where they are. That is because both of these instructions depend on the RCX, the updated RCX value, which is currently being executed in the second move instruction. In the next cycle, the call instruction, so now the move instruction will be executed and the RCX value will be updated. In the next cycle, the call instruction moves forward, but the compare instruction stays where it is. And that is because even though RCX has been updated, its ISA state has not been updated yet. So the registers have not been written yet. Now in the next cycle, the RCX value will be updated, following which it will be updated, will also be reflected in the bottom half pipeline. And then from this point onward, the compare instruction will proceed, followed by the fail instruction now being added to the fetch stage. And then the execution smoothly continues. And then based on whether or not the compare passes, the call instruction in the top half pipeline will retire accordingly. So the bottom half pipeline will notify the top half pipeline whether or not to retire the call instruction. So this basically illustrates how a sample CFI monitor could in principle work on a sample monitored thread. Now let's talk about the related work. So TEs have been deployed out there in the real world. I mean, SGX already is being used by Intel. Is being used by Azure, and also being used by Signal for that matter for their contact discovery feature, which is a very sensitive feature in Signal. A sibling of SGX is ARM's equivalent, which is the trust zone. But a key difference in ARM is that it has a special added mode called the Secure World Privilege mode, where any computation running in this mode has access to everything. which also makes trust zones slightly ill-fitted to the data center model, where we assume that the data center itself is untrusted. So having this particular mode in hardware that can access everything doesn't really align well with the vision that these have. Now, a piece of academic work which is very relevant to our research is Sanctum, where Sanctum implements enclave isolation via an open source monitor that runs in RISC-V's machine level. However, Sanctum does not provide a software readable description of the underlying microarchitecture. Now, just like IME, Sanctum also provides cache level partitioning for the enclaves that it creates. However, it doesn't yet provide isolation at the microarchitectural level. So all of this microarchitectural state is still shared in the Sanctum approach, which again makes it susceptible to side channels due to hyperthreading. But the most important difference between Sanctum and IME is that Sanctum has no mechanism to perform runtime integrity checks on the computation that is running inside an enclave. Now let's talk about the open challenges. So the first most important open challenge is the side channels that can arise from monitor-induced stalling. Now, a couple of ways to address this would be, one would be constant time execution, where the runtime of the top half code is tailored such to the worst case execution time of the monitor checks, so that there's no variability based on the number of stalls or that are induced by the monitor. The second would be early launch of monitors, where a monitor can start executing a check even before the corresponding top half instruction has begun its execution. But again, it depends on the top half ISA level register state being ready for the bottom half pipeline to perform that check. The second piece of challenge is how do we reason about high performance network IO, because in order to perform IO, again, the hardware will have to switch out of monitored mode to non-monitored mode, just like SGX, and which will have a significant performance overhead. The third challenge is multi-threaded applications. So currently every thread in IME has its own monitor, but could we come up with an approach where sibling threads can actually share a monitor to reduce the overhead and yet not have any side channels at play? Fourth challenge is syscalls, which is again similar to IO, because again for syscalls, the hardware will have to switch in and out of monitored mode, which will incur significant overhead. Another scalability challenge is diode migration. So in a data center setting, anytime a top half thread, a computation running in the top half pipeline has to be migrated, then there's an additional state of the monitor running in the bottom half that also needs to be migrated. So clearly there's more state that needs to be managed, which will again lead to some overhead on that scale. And then last but not the least, all of this added hardware will lead to an additional die area. And then how do we reason about the power consumption still remains an open-ended challenge. So in conclusion, we basically showed how the IME approach can isolate secure computation from all other local computations, especially including the privileged ones, and also perform enforce dynamic runtime checks to demonstrate to the end user that their secure computations are actually secure. And then the third goal is, which is still is work in progress, where we are working on a software readable description of the microcode through our implementation in Chisel. And that essentially summarizes our work so far on IME. Thank you for your time.